So I'm going to tell you a little bit about a failure from my professional life. It's a little f failure, thankfully, not a big F failure. I'm failing to put this on correctly. Hold on one second. Okay, there we go. So I am a planetary scientist and astronomer here at MIT. And I wanted to just start off tonight by telling you a little bit about someone who's really important to me, my scientific mentor during my undergraduate and graduate days. His name was Jim Elliott, and he was a professor here at MIT until he passed away in 2011. And I learned a lot of things from Jim Elliott, and one of the things he taught me was how not to fail. And this is how he did it. I would go with him on observing runs, so we're both planetary scientists, both astronomers, and we would go to the telescope. And so my idea of going to the telescope is going to the telescope, sitting down and saying, well, what should we look at? Definitely not Jim's idea of going to the telescope. Before you go to the telescope, you spend weeks putting together your observing plan. You have an observing plan. You have a backup observing plan in case something's wrong with that one. You might have a third backup observing plan. You have everything totally planned out. You have finder charts. You know everything that's going to happen on that evening. After you get your data, you make 3 copies of the data. I take one home with me. He takes one home with him on the same plane. And so because we're on the same plane and that plane could go down, we mail the 3rd copy, right? We often were observing where we had to bring our own equipment, and it was specialized equipment because of what we were doing. So that equipment might get lost even though we're carrying it, and so we would bring backups. The backups would not be in the same case as the original because those could get lost. So we want to have, backups in a separate case, something that if we can't buy it locally, we brought backups with us. He even went so far when he got a new calculator, he would test the calculator to make sure that it did math correctly. How many people have done that? Pretty much. I see a couple hands, so that's pretty good. Well, he once found a calculator that didn't do math correctly, so he was vindicated in that, even though I pretty much thought he was crazy. So, until that happened. So I learned a lot from Jim about how to really be prepared. And it really, I have to say, this level of preparedness, this sort of 11 on the scale of 1 to 10, it is not my natural inclination at all. But I learned it from him because it was necessary for the kind of work that we do. And so let me just tell you a little bit about what it is that I do, and then we'll get on to the next part. So I said I was a planetary scientist. I study small, cold bodies in the outer solar system. And I use a special technique called a stellar occultation. And what a stellar occultation is, it's a body passes in front of a star. You're actually watching the starlight, and the star blinks out, and you learn about the body from that star going away. It's kind of like a solar eclipse, but further away. The important thing to know about this is it's an experiment that you have no control over, because it's just really up to the universe to put things in the right order, because everything is moving. The Earth is moving, it's spinning on its axis, moving around the sun. The planet, or whatever it is you're trying to observe, it's moving. Even the stars are moving. We think of them as not moving, but they're moving too. Everything is moving, and then every once in a while, star, planet, Earth line up, and it's magic. And a shadow is cast in starlight, and that shadow falls on the Earth. And it's my job as an astronomer to make sure that I or my team are in that shadow at the right time, in the right place. The shadow is usually smaller than the Earth, so we need to be there observing so we can learn about the body that is casting the shadow. And if it works, then we get amazing data. We can learn about the body that is blocking the starlight, so we learn about planets or asteroids or Kuiper Belt objects. We can figure out how big they are, what their shapes are, if they have atmospheres. And the kind of data that we get is really high resolution. The only way you can get this kind of high resolution is by sending a spacecraft there, if not through occultations. So the critical thing that makes it difficult to do this is really targeting. When is that alignment happening? Where does that shadow fall on the Earth? And so you need to be really, really incredibly accurate in figuring out where all of these moving pieces are in order to do the prediction so we can figure out where on the Earth we need to be. So to explain how accurate you need to be, I forgot to bring a quarter, but imagine I'm holding a quarter, okay? And then imagine I'm going to give this to my colleague, and my colleague is going to stand in lobby 7, and they're going to walk slowly with this quarter. Now, I want to figure out the position of this quarter, and I'm going to stand on the other side of the infinite corridor with a laser, and I'm going to try to target that quarter on that moving platform very accurately from the other side of lobby 7, from the other side of the infinite corridor. So it's difficult. You have to be very precise in your targeting and make sure that you're really hitting it very accurately. And it's hard, but it's not impossible. And so that's great. And that's the kind of thing that we do in order to predict these occultations, except we have to be 20,000 times more accurate than that. So in order to do that, you just think of moving the observer back from the edge of the infinite corridor, back a bit more, all the way to California. And that's the kind of accuracy that we need, being able to target a quarter in lobby 7 from California. No problem. All right. So the kind of effort that goes into predicting this requires an immense amount of work. For one particular event that I'll tell you a little bit about, we worked for 2 straight years doing almost nothing else to predict this, and in order to be in the right place to observe this particular occultation by Pluto, and the entire event lasted 3 minutes. So 2 years worth of work in order to see something that lasts for 3 minutes. This was in 1988. I had just started graduate school, and we were trying to observe this occultation by Pluto, the first one. And we observed it successfully, thankfully. And from this event, we learned that Pluto has an atmosphere. That atmosphere is made out of nitrogen, methane, a bunch of other things. We could figure out the temperature structure. We got a lot of information. I'm not going to bore you with all that information. So the preparation for this, what I learned from all of that preparation, is the possibility of failure, how close failure was at every time. Because we were working hard, we knew what we were doing, but failure was just around the corner every single time, every day, and we were always aware of it. So I'm going to fast forward to 2011. It was a bit of a difficult year. It was a very difficult year for us because that was the year that my mentor passed away, and we had a very close working relationship. I worked a lot with him, so it was very sad to lose him. And the other thing that was sad was that we lost him just before our next really big Pluto occultation, and I know he would have been so excited about this. He was really working for it, and so I was sad for him as well. And so our Pluto occultation we were doing in 2011, let's see if this will work. We were using the Next Generation Airborne Observatory. This is called SOFIA. It stands for Stratospheric Observatory for Infrared Astronomy. It's a 747, and you take a nice, perfectly good 747, you cut a hole in the fuselage there, and in that cavity you stick a 2.5-meter telescope. And this is an excellent observational platform. They've done really great work with putting this together. It works great, and scientists have done a lot of great work with it. It can fly up to 45,000 feet. You get above all the water in the atmosphere. You can move around. You can be where you need to be to see something. It's also, because you can imagine there's pilots, there's scientists, there's engineers working on this, it costs $1 million per flight. So in 2011, we were granted a flight on SOFIA so we could observe a Pluto occultation. So we didn't have to pay the $1 million, but just knowing that that's what it cost was enough to fill me with the little f fear. And so it was my job to put the plane in the right place so that they could observe the shadow. If we were in the wrong place, we would see absolutely nothing. We monitor the light from the star, and if we're in the wrong place, you don't see anything happen. You just get a flat line. You learn nothing about the body. You don't get like a partial solution or maybe an ambiguous solution. You just get nothing. So I really had a lot of motivation to do this prediction correctly. As I was working on the prediction, I was definitely feeling failure's presence every single day. What happens if I get this wrong? What else should I check? What needs to be? What do we need to do? What do we need to do? What do we need to do? So the night before the occultation comes, I'm working with my colleague Carlos. We're the astrometry team. And we're making measurements of Pluto, figuring out where it is. And so finally we get our final prediction, and we call the plane. They've already taken off, and we say, you need to fly 200 kilometers north of where we told you to go yesterday because the prediction has shifted. Please just trust us on this. And so they say, okay, they do, and they're off to catch this occultation above the South Pacific Ocean near New Zealand. So at this point, we've already told them we've done our job. Carlos and I are sitting there. We have to wait 7 hours before we figure out what happened, if we were successful or not. 7 hours is a long time to wait. 7 hours. In 7 hours, you have time to re-reduce all of the data you took that you've already reduced 10 times, but you have time to re-reduce it more. You have time to second-guess yourself roughly 125 times and to think about all the things you could have done wrong and how you might have done something different. During this time, I also spent some time thinking, what would Jim have done? What am I forgetting that Jim would have noticed? I really, really wanted, I wished he were there because I'd often, in times like this, I'd often toss ideas back and forth and say, well, what about this? This looks odd, do you think we should include it? What about that? And the reality was he was gone and we were on our own, and so we had to just go with what we had. So we finally get the word back from the airplane after 7 hours, and it was a success. And we were so overwhelmed with emotion. And for me, the most important emotion of that night was relief. Thank God I didn't mess this up. We got the data. We went on to analyze it and learn about Pluto's atmosphere. At that time, it was still there. It hadn't disappeared yet, so that was good. And then, so we went on from there. I've had, in terms of occultation predictions, I've had other successes after that, some of them on Sophia. And our most recent Sophia flight was just last September. I'm going to just finish off with a little bit of information about that. It was September 2018. We were observing an occultation by Varda. Varda is a Kuiper Belt object, so it's beyond Pluto. And it's a possible dwarf planet, but we really didn't know because there weren't a lot of observations about it, so we needed to do this occultation to figure it out. We needed to find basic information, size, shape, did it have an atmosphere, did it have rings? So we went through the same procedure, ground-based observations, figuring out the prediction, revising the prediction, calling the airplane, telling them to move, and then going on with the observations. This one was a little different because it was over the American Southwest, so we had a lot of ground-based telescopes as well. I was on one of them. And so we were getting data in, and we saw, yes, this is working. Yes, we should have a chord here, and we have a chord. Yay! We were very, very excited. And we figured, okay, great, Sophia's going to get a chord too. And then they called us, and they didn't get a chord. And I still, right now I'm saying that, and I'm like, I still feel the emotion that I felt on that day. My heart dropped to my feet. I'm like, how is that even possible? How is it possible that they didn't get a chord? We all got chords. They should get a chord too. How is it possible that I failed? And yet it was true. I had failed. This very expensive observatory was either in the wrong place at the right time or in the right place at the wrong time. I wasn't sure. And so I kind of tried to get over that immediate feeling of failure and then got to work. What's going on? Got the data, started analyzing it, fitting ellipses. What could possibly be wrong? Finally, we figured out that the actual shadow was 1 sigma to the west of the predicted shadow, and that was enough to take Sophia out of the chord, out of the shadow. So they got no data whatsoever. And we're thinking about it here, right? 1 sigma. That's 1 sigma is 1 sigma. Things are going to be outside 1 sigma 35% of the time. No big deal, right? And none of that mattered to me. It still doesn't matter to me. I got it wrong. That's what mattered. That was my first failure on Sophia. But we continued analyzing the data, and we realized that Sophia chord actually gives us a really strong constraint of how big Varda is. And when we went into this, that's what we wanted to know. We wanted to know how big is Varda. And Sophia got a non-detection, but that non-detection was a really important non-detection. It actually puts a limit there. It can't be any larger than that. So we managed to pull success out of this one particular failure. It doesn't always work out this well, though, so I'm really grateful that it did in this particular time. I find that I often learn something from failure. Sometimes it is something really simple, like don't try to observe during the rainy season. not a good idea. Sometimes it's something more important, like how to prepare better for the next occultation. And sometimes we actually get new things out of it. Like from this particular one, we actually realized that a technique we were using could also be used to discover binary Kuiper belt objects. So we're going forward with that as well. So in looking at my career, one of the most important things I learned from Jim, my mentor, is how to fail successfully. Now, I did not always fail successfully. Sometimes I failed unsuccessfully, spectacularly. But I also learned that failure is okay, and it's a natural and necessary part of the scientific process of pushing the envelope. It's hard to really continue pushing the envelope if I'm always working safely. So, for myself and for all of you, here's to many successes and to many failures. Thank you.